Drop a 5-gram solid iron nail into a glass of water, and gravity pulls it straight to the bottom. It sinks instantly. But out in the ocean, a 100,000-ton aircraft carrier, constructed entirely of solid military steel, floats effortlessly on the surface. Gravity is pulling relentlessly downward on the mass of both objects. For that massive ship to avoid plummeting to the seafloor, a counterforce of equal magnitude must be actively pushing it upward. Physicists call this upward counterforce buoyancy, or upthrust. The question is, why is this invisible push strong enough to hold up millions of pounds of steel, but entirely incapable of saving a tiny nail? The answer reveals that floating has almost nothing to do with being naturally lightweight. It requires highly specific engineering to cheat gravity. To see how this works, we have to dive deep beneath the surface and look at the behavior of static fluids. Underwater, the surrounding liquid presses against an object from all possible directions at once. This animated diagram shows these interacting forces. Arrows represent fluid pressure. Because water has weight, pressure naturally increases with depth. Therefore, upward pressure pushing on the bottom is strictly greater than downward pressure on top, creating a net upward push. Every single object placed in a liquid is trapped in this exact physical tug-of-war, gravity pulling the mass down and a pressure differential pushing the volume up. The Greek mathematician Archimedes figured out who wins that tug-of-war. He discovered that the magnitude of the buoyant force is perfectly equal to the weight of the fluid displaced. This technical diagram illustrates the classic experiment. When an object is suspended from a spring balance and lowered into a Eureka can, the scale shows a weight loss. That lost weight precisely matches the physical weight of the overflowing water. Applying this to our iron nail explains the paradox. The nail is small and solid, meaning it displaces a very tiny volume of water. The physical weight of that displaced water is significantly less than the iron, so gravity wins. A ship is engineered differently. Its hull encloses enormous hollow space, forcing it to displace a colossal volume of water. This drops the ship's average density below seawaters. The weight of that displaced ocean perfectly balances the steel's total weight. You don't need light material to float. You need geometry and volume to command enough displacement. This brings up a challenge. How do you sink and float on command without altering your vessel's shape? The submarine is the perfect example of dynamic buoyancy control in action. Submarines are built with internal ballast tanks. To dive, the crew floods these tanks with seawater, increasing the vessel's average density until sinking. To surface, they blast water out with compressed air, dropping the density so the sub rises. Human engineers borrowed this exact mechanic directly from the natural world. Fish navigate effortlessly by inflating and deflating internal swim bladders to manipulate their own density. The mathematical rules of displacement apply to every fluid, including the gases in our atmosphere. When you fire the burner of a hot air balloon, the air trapped inside the envelope is heated, causing it to expand and drop density. Because the air inside is now lighter than the surrounding atmosphere, the heavier, cooler outside air pushes its way in underneath, forcing the entire balloon upward. We live our entire lives submerged at the bottom of an ocean of air. By mastering the strict mathematics of geometric displacement, we engineered the ability to conquer both the seas and the sky.